Hello everyone, welcome to the second part of this tutorial for Naphta simulation of Naphta desulfurization in ASPEN Plus. In the first part, we simulated our reactor where these we desulfurize these sulfur compounds, and the products are then cooled to 35 degrees C, and then they are passed to a flash drum. So the flash drum removes the gases. The heavy components were actually condensed down, and the gases for obtained is the vapor. So that vapor feed is then passed through the absorber, and in the absorber lean this amine is used to remove the hydrogen sulfide, and the rest of gases are recycled to the process. Similarly, these heavy components, they are sent to a distillation column where the remaining gases are removed, and here we obtain our desulfurized product. So we shall continue our simulation in ASPEN Plus. So first I will install the session column. So click on column and click on this red flag. Select this icon, red flag. Okay, and feed this stream to the red flag, right? Okay, this is, and we have top product is vapor. This is a partial condenser, right? And we have bottom product. Okay, now double click on this distillation column. There are 25 stages. This is a partial vapor condenser, and the reflux ratio is 3, and the boil-up ratio. This boil-up ratio is 1.2, and the reflux ratio is a 3. Okay, this is feed. This is fed to the stage number 15, feed stream, and the pressure is it is operating at a constant pressure of 1 bar, right? So run the simulation again and ensure that the column is converged. So you can see that the results are available. Click on view flow sheet and double click on this column. Okay, it is advised to rename this to distillation column. On distillation, just call this list. Double click on this, and now you can see in the results, stream results, mole friction. So this is the bottom product and this is the top product. So you can see that the top product contain mostly gases, and the bottom product contain the liquid, the desulfurized component. You can see that there are no desulfurized component in the bottom product. It has only desulfurized components, and the gases are collected as the top product. Okay, this stream is further cooled to an exchanger, and this stream is further cooled to, let me call this HX4. And this stream is cooled to 40 degrees C, right? C, and there is no pressure drop. I run the simulation again. So you can see that we need to remove, click on this results, we need to remove this amount of heat in kilowatt. 98 kilowatt heater to cool this to 40 degrees. Okay, now we are going to install an absorber. So click on this red click and select this icon for the absorber. Okay, let me call this absorber, and this is feed here. Okay, and we have another feed. This is actually the lean amine. Let me call this lean amine. Okay, double click on this lean amine, and this temperature is 25 degrees C. Pressure is 4 bar, and it's flowing at 50 kilomole per hour. And the mass fraction is this is 100% pure amine. Okay, now click on next. And, sorry, you need to add the product stream. So this is the distillate top product stream, and this is the bottom product stream, right? So double click on this absorption tower. We have 20 stages, right? And there is no condenser, no reboiler. Okay, and the lean amine is entering at this lean amine is entering above stage number 1. Okay, and this is on stage number 20 on stage, and the pressure is a 4 bar, right? Okay, go to the this convergence and click on convergence, and here raise this to 200 maximum iteration. Click on home and run the simulation. Okay, if you get some errors, so click on OK, and in this go back to the convergence and go to the advanced, and from here in the absorber select yes, reset it and run the simulation again. Okay, now you can see that results are available. So if I go to the results, stream results, here you can see that the H2S is now removed, this small fraction. Okay, and you can see that there is no H2S in the product stream. Okay, now go to the flow sheet again, and here we need to install a purge. So click on this mixer splitter, this F split. Okay, and feed stream to product streams. Okay, double click on it, and split friction is 0. This is 0.1. So this is actually the first stream. This is 0.1. We need this first because if we don't purge this, the unreacted components, those will be again recycled and recycled, and those will be accumulated in the process. So we need this purge on, and run it again. Now go back to the flow sheet. So this was our purge, I guess. This 25 is the purge. We just call this purge, right? And this stream is recycled. Okay, before we recycle this to the mixer, it is passed to a compressor. Let me call this compressor 1. and flip this. Just click on R and double click on this, and this is fed here. Okay, we need to compress this to 12.6 bar in the first compressor. So this is a compressor type isentropic compressor, and this is 12.6 bar. Okay, this stream is again this is you can see that the temperature of this stream is temperature. Okay, I just run the simulation, and the temperature is 148 degrees C. So we need to reduce this to 110 degrees C. Click on exchanger, heater, and click on R to rotate this. Let me call this as a so we want to cool this down to 110 degrees C, right? And there is no pressure drop here. So run the simulation again. Click on this view, proceed. Okay, if you don't want to see the temperature here, just deselect this, just uncheck this. Okay, now this is again compressed to 41 bar. So we need to install another compressor. This pressure changer, click on compressor. Okay, escape and click on R. Just press R to rotate this. And this is the product stream. Okay, let me call this compressor 1. This is HX5, and this is a compressor 2. Okay, we want to raise the pressure here to this is isentropic, and discharge pressure is 41. Okay, run the simulation again. You can check that double click on this and check the results, stream results. So the results of this unit operation. So this is the horsepower of this compressor. You can check in kilowatt or horsepower. Okay, now this stream is recycled to the mixer. So now I will recycle this stream to this mixer. Before that, just double click on this station column, and I think the convergence, go to the convergence and click on this convergence. Okay, just raise this iteration to 200, because sometimes if you have process that have recycled streams, so these columns are sometimes not converged. So it is recommended to choose the maximum iteration. Okay, now recycle this stream, double click on it and get this to mixer. Okay, now run this simulation. Okay, good. So that means that our process is now that means our process is converged, and the results are available. So you can see that this is our product. This is our product, right? This is our product. So you can check the product specification here, and here we removed the hydrogen sulfide, right? So now we are going to do the energy analysis. So before doing the energy analysis, we need to add the utilities. So go to this. Here you will find the utilities. This utilities, click on utilities and click on new. So utility 1 is water, is cooling utility. So this is just water, cooling water. Okay, and now it is asking you that water is not available in your component list, so just add the water to the component. Yes, and add another utility. Click on new, and this is LP steam. We call this LP steam generation. LP steam generation, and this is another cooling utility. LP steam generation. LP steam generation. Okay, this is a cooling utility, LP steam generation. Actually, this low pressure steam will be generated when we recover the heat. And another utility is this is fired heat. Let me just call this APH. Sorry, this is the utility type is fired heat. Let me just delete this and new fired heat. So this is fired heat 1000. Okay, this is the heating utility, and this actually gives you the energy price and the heating cooling value and the temperatures. However, leave this at the depart values. And another utility is HP steam, which will be used as a heating utility. Okay, this is HP steam. So this gives you the value of the energy prices and so on. This is the, if you want to change this energy price, like by depart, it says that it is available this much dollar per kg. However, you can change it here. Okay, now when you have added the utilities, run the simulation again. Okay, and click on this energy saving. So click on this analyze energy saving. Yes. So here you can see the total utilities. This is the actual, this is the target. This much can be saved using the heat recovery. If you just, this is the summary and the actual and the target. Like this is the actual utility. However, this can be reduced to this target. It can reduce to this when you do the heat integration or the when you install a heat recovery process. So these are the heating utilities, the cooling utilities, the carbon emission. If you click on utilities, so it gives you the fired heater. The current is this. This could be reduced to this. This is the high pressure steam. This is the current requirement is this. However, with the heat recovery, you can reduce this to this, and this gives you the percent energy cost saving. This is the energy cost saving dollar per year, and this one is the cooling utility, the water. Okay, and can also tell you about the carbon emission, and now we want to design heat exchange network for this system. We want to see that how can we actually recover the heat. So for that, go to the energy analysis and click on this. Okay, this is actually these are the process streams. Yeah, it has identified the process stream, the input and output temperature, right? Like in the heat exchanger one, temperature is raised from 38 to 250 and so on. So here in HX5, temperature is down from 145 to 110 degrees C. So this is the condenser of the reboiler. You can see this is the condenser of the reboiler. This is the condenser of distillation, and this is the reboiler of the distillation. So you can see that in some heat exchanger we want to raise the temperature, and in other heat exchanger we want to decrease the temperature. We want to cool some steam, and we want to heat some steams. So now click on this details and click on yes. So it will open ASPEN Energy Analyzer. If you have not used the ASPEN Energy Analyzer earlier, you may visit my channel, and there is a playlist which describe in detail how to use the ASPEN, what is ASPEN Energy Analyzer, and how you can use it to do the heat integration. So this gives you this. This is the another software is open. This is also the product of ASPEN, ASPEN Tech. So this is called ASPEN Energy Analyzer, or AEA. And if you click on this scenario, and these are the streams. These are the cooled and hot streams that the software have identified. This is the input temperature, the output temperature. This is the enthalpy of each and every stream. Okay, you can also check the utility stream. So these were the utilities, and this is the composite curve, right? And it can also tell you, if you click on the target, so it can tell you that how much heating utility and cooling utility is still required. You can check it here. You can also design the heat exchange network. Here, just click this recommended design and click on solve. Okay, it has just provided 6 design. Now you can check each and every design, and here you can see the cost per second of every designer. So we should select the design which has the lowest cost. So if you click on this says 3.4 into 10 raised to power minus 3 dollar per second. This is 3.04. This is 3.07. This is 3.11, and so on. So I will select this 3.07 design. Here you can see that all those heat exchanger which are which are blue. So blue means that heat exchanger is installed between this is image between the hot stream and the cooling utility, and the red heat exchanger is the heat exchanger that is installed between cool steam and a heating utility. Okay, so this is the heat exchange network, and you can also see some additional information here. There are 12 number of units. You can count these are 12 number of units, and there are 13 shells, and the total area of the heat exchange network is 79.61 meter square. So that's it. Thank you for watching. Please share this video with your friends, and if you have any question, please write in the comment section. Thank you very much.